Cool. So a really quick background. I spent the last several years doing primarily Scala development, and then over the course of the last few months, I've switched into primarily JavaScript development. It's been kind of an interesting journey for me. Hopefully this won't be too trivial for those of you who are familiar with JavaScript. I still consider myself very much a newbie. But with this talk, I want to go through just some of the lessons that I've learned by taking ideas and patterns from JavaScript and thinking about what I know about Scala and how they compare and sort of what some of the advantages or disadvantages might be. And then how I can fold that back into my Scala development to sort of improve myself in both languages. And I also want to caveat this or sort of disclaim this with, this is what JavaScript taught me about programming in Scala. So there's probably certainly going to be a lot of confirmation bias and anomaly hunting that I did looking for things that I wanted to learn. So I don't necessarily recommend any of these things to anyone but an audience of myself. So take that with a little grain of salt. So right off the bat, if you jump into the world of JavaScript, you'll find that there are a couple different ways that you can write it. These are all different languages that extend JavaScript in some way or give you a totally different syntax or language that compiles into JavaScript. And I think I like this because it sort of demonstrates the lack of consensus on how to write JavaScript. And there's sort of a similar thing in the Scala world. Oh, by the way, I'm going to go really fast through these slides because I have like 50 of them. So feel free to stop me at any time. I'll put on the brakes and go into detail. Otherwise, I'm going to zip through. So there's a similar pattern in Scala where, depending on your background, you'll come into Scala and say, hey, this just looks like simplified, cleaned up Java. Or, whoa, I can do type classes, and this is just like the Haskell that I know. And I've heard the same thing from ML developers, and I think you can even write BASIC in Scala with a DSL. And furthermore, the set of language features that Scala offers is pretty robust, and in SIP 18 they added this modularization, so you can choose which language features you want to use and which ones you don't want to use when you're developing Scala. And so from all of this, the lesson that I sort of took is there's a lot of options, and if you're on a team, especially a varied team with different backgrounds, you're unlikely to sort of come to an organic consensus on how to write your code. So the lesson is to sort of be intentional about picking the dialect based on who your developers are and what their experiences are and just sort of what the appropriate style will be. And then kind of move on and go forward. And in our case, this manifested as looking at these JavaScript languages, TypeScript especially, and finally saying, well, we're just going to write vanilla JavaScript and move on with our lives. Similar to this lesson is, rather than language styles, sort of patterns within the language. So for example, constructors in JavaScript look like this. And the idea is that namespacing and scoping in JavaScript is a little bit confusing for somebody who's coming from Scala. And when you're using this in JavaScript, you have to be careful to use new so that you're creating a new context under which this function is running. And so the way to instantiate a new object in in JavaScript is either like this or like this. And so the difference between object literals and constructors are that with object literals, you're not using new, you're not using this, you're just creating a literal new object and returning it. And again, there's not really a right or a wrong way. This is just illustrating a difference that I encountered and actually really confused me at first when I didn't know what was going on with the scope of this. Scala has similar sort of competing patterns, especially when it comes to implicit conversions. So for example, let's say we want to add functions to an existing type. In this case, we have int, and we want to add a squared function to it. The very simple way is to write a squared trait and then create an implicit conversion from int to an instance of squared that has a squared function defined. But another way we can do this is with full type classes, and that's where we are not only defining this implicit conversion, but we're defining a library that operates on values that have some conversion to that type, and then can then call that squared function on behalf of the original type. And again, there's not necessarily a pro or a con or an obvious choice between these two patterns until you start to look at external pressures and experience and other kind of stylistic preferences. So again, this is very similar to the first lesson, but the idea is that we have sort of a wealth of different options on the table, and we can kind of debate them and argue about them, but at some point, as a development team, we need to just sort of pick the set of conventions and patterns that we want to use and move ahead. In this case, I extended the audience bullet a little bit to talk about, because we are now talking about specifics of how we're writing our code, and so that's going to affect our APIs and affect our function signatures, and so people who are, depending on who's going to use the code, whether they're just the team members or third-party library users or even some kind of other API consumer, all of this kind of folds into consideration of what patterns you'll choose. Modularization is another big tricky bit in JavaScript. Actually, it's going back to that first slide with all those languages, there's a million different ways to do modularization in JavaScript, and it's mainly because there's not really a native way to do it. There's pretty much one global namespace, and it's very difficult to create non-global namespaces. So we primarily used node.js. So Node has its own module system, and it looks like this. So here I'm building a module and exporting one function from that module called square. But this wouldn't work if I were to use this code in a web browser instead of a Node app. So if we were using a web browser, it gets a little bit more noisy, but the pattern that's sort of generally adopted is something like this. So we have to deal with this global namespace, and to do that, we're taking some object, in this case it's called maths, and treating that as sort of a namespace that we can add things to. But it's the same idea. The point here is that it's different. And if you want to write a JavaScript library that works both in the browser and in a Node app, you have to figure out some way to combine these two, which is doable. It's just noisy and painful and tedious. Luckily in Scala, it's a little bit easier because we don't have all these different competing modularization standards. We pretty much have packages and objects, and then maybe traits or classes, depending on how you define a module. But again, there are still sort of these considerations to take, thinking about who's going to use the code that we're writing. Are we writing Scala code for other Scala users? And if that's the case, we're kind of free to use anything that we want, because Scala understands Scala. But if, for example, we're writing Scala code that needs to be consumed by Java developers through some API, we might be a little bit more limited because of the way Scala generates anonymous classes and appends $signs and things to the names of objects. Things like this are all sort of important to consider. And so this is the third lesson that's sort of in this same class, which is of all the choices that we have to sort of intentionally pick an ecosystem that fits our particular use case. So in this case, the considerations are, do we need this to work in Maven or SBT? And if so, what are the implications? Will we be using third-party libraries, and do those impose sort of modularization restrictions? And on and on and on. Continuous integration, release processes, third-party users and consumers, et cetera. Okay, so now I'm getting more into the code itself. I'm primarily a Vim user, so I tend to have my code open in Vim and then some kind of build tool open in a terminal, and that's about all I do. So for me, Scala adds a lot of value in that I can continuously compile it, and when I have syntax errors or compilation errors, I see them right away. But this isn't the case in JavaScript because there is no compiler, right? Generally, if you make, in this case, I forgot to capitalize the W when I called hello world, and I would only find out about that at runtime. Of course, lots of tools exist to help you, and the one that we were using was called JSHint, and it's just a typical code linting tool. And so like with Scala, you can run this thing continuously, and it will look at your code, do static analysis, and catch. In this case, it catches two problems. It says, hey, you're calling a function that doesn't exist, and also you wrote a function that's not called. So both of those point to the problem of me fat fingering my invocation of the function. So Scala also has code linting tools. The biggest one, in my opinion, being Scala C. If your code doesn't compile, that's a big indicator that something is wrong with your code. And then there are other tools. Scala style is like the Java check style, in case you're familiar. But it lets you define coding conventions that you want to adhere to and then enforce those. And then wart remover is a pretty cool one, which is similar, but sort of comes with its own, at least out of the box, comes with its own suggestions about what your code should and should not do. And I really like wart remover because it's a SBT plugin and it executes at compile time. So you can come up with whatever standards are appropriate for your team, like thou shalt not use var or whatever, and then that gets enforced at compile time. And so you can catch problems like this early. And so the lesson learned from all of this is do static analysis. The compiler in Scala is your friend, and the earlier you catch a problem, the faster you can move. And so for me, that means I use a lot of triggered execution. So as I said, I'll have my editor and my terminal, and in my terminal, I'm usually running SBT with some combination of tilde and a command. So test is a common one, but compile would work as well. And this way, anytime I'm updating the code, I'm running Scala C and then any other tools like Scala style or wart remover that I might have integrated. And then any sorts of convention enforcement that can be done automatically should be done automatically. So I shouldn't have to run JS hint from my terminal when I can integrate it into my tool set, integrate it into my continuous integration, and so forth. Okay, so can anyone guess what this function does? This is a JavaScript function for which I've hidden the implementation. The short answer is no. There is absolutely nothing you can infer about this function just from looking at the signature of the method, except for maybe that its name is foo. And I would love to go into why, but I don't have enough time. So what about this one? This is a Scala function. It's almost the same, but Scala makes us put a type annotation on the argument. And in this case, I've added one to the return type. So we know a little bit more about this function. It does something with integers, whereas this function does who knows what with anything. So we can start to guess what this does. Maybe it takes x and doubles it. Maybe it just returns 42 and ignores x. So let's see if we can make this better. So now we've thrown a type parameter in there and gotten rid of int. So now we say the function foo is parameterized on a, and it takes an a and returns an a. So surely some of you have seen this, but can anyone guess what this function does, just from the type? Right, yeah. So this says for any possible type A, which I don't know what A is, I the function, I will return you an A. And the only possible way to get an A when you don't know what A is to return the one that comes in. And this is ignoring cases like null or throw exceptions or whatever. So the answer is this function can only possibly return its input, so it is the identity function. And this is just a little peek into a very interesting field called parametricity. And I really recommend you read the paper Theorems for Free by Wadler if you're interested in learning more about this. But basically the lesson is, I said use generics, but really I should have said be judicious about your type annotations and use generics where you can. Because it really constrains the scope of what a function can do. And because of that, it communicates a huge amount of information to other developers who might be future you or current team members. And so forth. Okay, let's talk about testing. So JavaScript doesn't have a compiler, as I mentioned. It does have code linting tools and so forth, but testing in JavaScript is hugely important, especially when you're talking about refactoring or just asserting correctness of your code. Imagine you have a huge JavaScript project and you want to rename a function, fairly simple operation. Well, you go and rename it, and then what? How do you know that you've propagated that change everywhere it needs to be? At least for me, when I was first getting into JavaScript and I didn't know a lot about the tools, I would run it and kind of see what happened, and it would fail, and it was very frustrating. So I learned quickly that testing is really, really important. so that when I do introduce a problem like refactoring or anything else, I can catch it quickly without having to deploy my system and wait for a user to find the problem. So even though Scala has a compiler and it has these other tools, testing is still really important. The type system is great, generics are great, but Scala is not a theorem prover, right? It's not Coq, it's not a fully path-dependent, it's a Turing-complete language. So there can always be problems in your code. So testing is still maybe less critical than in JavaScript, but still pretty important. And when you start thinking about tests as being so important, they actually start to buy you a lot. So you can reuse them. And what I mean by reuse them is if you write a set of tests and you say, this is what my system should do, you can take those tests and say, hey, here's some documentation. Maybe it goes in the examples section of your README, or maybe it literally becomes the documentation of how to use your system. And then you can take it one step further and say, you know what, we only want to officially endorse the functionality that's behind our tests. And in that case, your tests actually become the official specification of your software. And then you can start doing things like versioning by specification, and it gets really interesting. It has tons of benefits. And so I guess the lesson from all of this is where you can, emphasize tests, but where you can, develop from the tests. And so then you don't have to argue that 100% code coverage is good. It's awesome when you get there, but it's totally not needed, and it's not always practical. But if you are making the tests your official standard, then you're guaranteed to have 100% coverage of your specification. And that's pretty handy when it comes to preventing bugs in the specification from going out. And then it also opens you up to really start changing the way you think about changes that you're making to your system. So when people are reporting issues, you can start to redefine what bug means and what feature request means. To the point where if your specification tests are all passing and somebody reports something that they dislike for whatever reason, you can call that a feature request and not a bug, because as specified, your system works great. It's a little bit hand-wavy, but it does make for a very effective version management and release management strategy. Okay, mutability. I'm sure you can guess where I'm going with this one, but when you have mutability, unexpected things can happen. So here's a really dumb example where I have a date data type with a year, month, and a day, and I have a function that computes a date with for the next year, for the following year. And because I have this plus in there, it's actually modifying the incoming data. And so this function is not referentially transparent because it does return the correct thing, but it mutates the input value. So I can't call it more than once without basically breaking the input data. In Scala, we can get around this with case classes, which are immutable by default. And so we can write the same kind of thing and be much more confident that we're not going to accidentally, because maybe when we wrote this, we didn't understand the semantics of that it doesn't just compute a new value, but modifies the original value. But in this case, we're not going to accidentally fall into that trap. And so it's much easier to write a referentially transparent next year function when all of our code is, all of our data is immutable. And then in a similar vein, when we start to talk about multi-threaded systems, mutability becomes even more of an issue. Fortunately, in Node, in many cases, your entire application is a single thread. So you can get away with a lot of stuff, like maybe I want a hit counter on a HTTP request service function. And I can do really nasty things like this. This would be totally unsafe in a multi-threaded system because we're changing hit count based on hit count, and the hit count itself could change while we're trying to change it because of another process. So to get around things like that, we can do things like make data structures that allow us to treat immutable data as though it were mutable. And that's, for example, the state monad would let us do that. And that buys us a lot in terms of being able to reason about code that in a sort of imperative mutable way, but have it still be safe and immutable. And you could do this in JavaScript as well, but it would be pretty messy with the types or the lack thereof. So I'm just about out of time, and I have quite a bit to go, which is unfortunate. So let me just scroll through these real quick, and I'll just talk about each of the lessons. So in this case, the lesson learned is avoid mutability where feasible. So I also talk about, and I will publish these slides for anyone who's interested in reading more, and I'll also be around to answer questions since I am going kind of so fast through these. But in these slides, I'll include the rest of these lessons that I'm rushing through. So one of them is configuration via code. So using actual Scala to configure your Scala application instead of properties files or .ini files or whatever. I talk about documentation and why it's important to publish that. And I even talk about why you might not want to use Scala in certain cases. For example, startup performance, popularity, ecosystem adoption. There are all kinds of considerations that you need to think about. I wish I had time to talk about deployment. Deployment to Sonatype is really, really painful, and Node with the Node package manager, I think, gets it totally right. It's wicked easy to deploy NPM modules, and I think that actually leads to more adoption. Cool. So sorry I didn't have too much time, but are there any questions on what I did cover? Yeah.
About your point about testing and making your test to specification, let me play devil's advocate here. Like, assume you write a library that exposes a square function. Right? It takes an integer and returns the square of that integer. Now, you're writing a couple of tests, and that's fine. And then they say, hey, if I use this with 10, it actually returns 100. It returns 101. Right? Now, you happen to not have this in your test. So you're going to tell me, oh, well, nice new feature request. It's probably a feature we should implement.
Right.
That's probably the point where I would drop using that library.
Okay, that's fair. So, well, so the question is, when we're talking about tests as specification, it's pretty important to get the completeness of the tests right. Because if we write a square function and we test that 7 times 7 is 49 and 1 times 1 is 1, right? But we don't test 10 times 10 is 100, and then it turns out there's a bug in that particular case, users are not going to like that. And if we come back with, well, we didn't specify that it could square 10, right? It can only score 1 and 7. Yeah, that's awful, and that therein lies the trade-off. So getting your tests, if you're testing, well, if you're writing functions that operate on very wide ranges of data, like integer, your best bet is going to be something like property-based testing or something like that. But yeah, you're not going to catch all the cases. So I think that's a good point, and maybe a follow-up to that would be try to use algebraic data types where you can to limit those kinds of problems. But yeah, it's a valid concern. Cool, thank you.
Thank you.